Imagine a world where your morning coffee could be both hot and cold at the same time, where a single coin flip could land on both heads and tails simultaneously. Sounds impossible, right? Welcome to the quantum realm, a universe so bizarre, so counterintuitive, that it makes even the wildest science fiction seem tame. Before we can even begin to grapple with the mind-bending phenomenon of quantum entanglement, we must first plunge head-first into this quantum soup. Forget everything you think you know about how the world works, because down here, at the level of atoms and subatomic particles, the rules are different. It is a realm governed not by certainty, but by probability, a world where things can exist in multiple states at once, a concept known as superposition. Think of it like this. A quantum particle is not a tiny billiard ball with a definite position and velocity. Instead, it is more like a blurry cloud of possibilities existing in a haze of potential until someone or something, looks at it. One of the cornerstones of this quantum weirdness is wave-particle duality. Is light a wave like the ripples spreading across a pond, or is it a particle, like tiny bullets fired from a machine gun? The answer, incredibly, is both. Light, and indeed all matter, can exhibit both wave-like and particle-like properties depending on how we choose to observe it. It is as if reality itself is playing hide-and-seek with us, revealing different faces depending on the questions we ask. This might seem like abstract theoretical mumbo-jumbo, but it is crucial to understanding how entanglement, this spooky action at a distance as Einstein famously called it, is even conceivable. Without grasping superposition and wave-particle duality, entanglement becomes utterly incomprehensible. We are talking about a universe where reality is not fixed, where possibilities abound, and where the very act of observation can fundamentally alter the nature of existence. Prepare to abandon your classical intuitions, because in the quantum realm, the only constant is the unexpected. We are about to journey into a place where the seemingly impossible becomes reality, where the very fabric of space and time seems to bend and warp. Are you ready to dive in? Because the deeper we go, the stranger things get. So we have plunged into the quantum soup, wrestled with superposition and wave-particle duality. But what happens when even the greatest minds struggle with these concepts? What happens when the very foundations of reality, as we understand them, are called into question? It all started brewing in 1935, a time of global upheaval and scientific revolution. Albert Einstein, a name synonymous with genius, found himself deeply troubled by the implications of quantum mechanics. He couldn't shake a feeling that something was missing, that the theory, despite its successes, was somehow incomplete. It wasn't that Einstein rejected quantum mechanics outright, but he resisted the idea that it offered a complete description of reality. He famously said that God does not play dice. This wasn't a theological statement, but an expression of his belief in an underlying order and predictability in the universe. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a now legendary paper that challenged the very heart of quantum mechanics. It was a bombshell disguised as a thought experiment, a deceptively simple scenario that revealed a profound paradox. This paper, forever known as the EPR paper after its authors, didn't directly attack quantum mechanics. Instead, it argued that if quantum mechanics was correct, it implied something truly bizarre, something Einstein couldn't accept, spooky action at a distance. The EPR paradox centered on the idea of entangled particles, those quantum entities we touched upon earlier, intrinsically linked regardless of the distance separating them. Einstein, Podolsky, and Rosen imagined a scenario where measuring a property of one particle instantly determined the corresponding property of its entangled partner, even if they were light years apart. Imagine two gloves, one left and one right, placed in separate boxes. You send one box to Alice on Alpha Centauri and keep the other. When you open your box and find the left glove, you instantly know Alice has the right glove, even before she opens her box. Now, Einstein wasn't arguing against the fact that these correlations existed. Experiments showed the correlations. His problem was the instantaneous nature of the connection. How could one particle know what the other was doing, seemingly faster than light, which is supposed to be the ultimate speed limit in the universe? He saw this as a violation of what he called locality, the principle that an object is only directly influenced by its immediate surroundings. Einstein proposed that the correlations were not due to some mysterious quantum link, but rather to what he called hidden variables. These would be pre-existing properties that the particles possessed from the moment they were created, properties that determined their behavior regardless of any measurement. This meant that the particles weren't actually influencing each other instantaneously. They were simply revealing predetermined characteristics. It would be as if those gloves were always destined to be left and right, even before they were placed in the boxes. The EPR paper wasn't just a critique of quantum mechanics. It was a defense of a particular view of reality, a reality that was local, realistic, and predictable. Einstein believed that the universe had an objective existence, independent of observation, and that quantum mechanics, with its inherent uncertainty and non-locality, was failing to capture this fundamental truth. He felt that quantum mechanics was a powerful tool, but an incomplete picture. He suspected that beneath the probabilistic surface lay a deeper, more deterministic reality, one governed by these hidden variables. Einstein's discomfort with entanglement wasn't simply a matter of physics. It was a battle for the very soul of science, a struggle to define the nature of reality itself. And so, Einstein laid down his challenge, a gauntlet thrown before the altar of quantum orthodoxy. But who would rise to meet him? Enter Niels Bohr, the Danish physicist, a towering figure in the development of quantum theory and a man utterly convinced of its completeness. What followed was not merely a scientific disagreement, but an intellectual duel of epic proportions, a clash of titans over the very soul of physics. Their debate would rage for years, playing out in conferences, letters, and scientific papers, shaping the very foundations of our understanding of the universe. Bohr, the architect of the Copenhagen interpretation, had a radically different perspective. This interpretation, which became the dominant view among physicists, argued that quantum mechanics was not incomplete, but rather described reality as it truly is. It embraced the inherent uncertainty and probabilistic nature of the quantum world, not as a deficiency, but as a fundamental aspect of reality. It posited that a particle does not possess definite properties, like position or momentum, until a measurement is made. Before measurement, the particle exists in a superposition of states, a cloud of possibilities. Think of it as a musical note existing as all possible frequencies until you pluck it from existence. Bohr countered Einstein's objections by emphasizing the crucial role of the observer and the act of measurement. He argued that it was meaningless to speak of a particle's properties independently of the measurement process. The act of observing, of interacting with the quantum system, inevitably disturbs it, forcing it to choose one state from the multitude of possibilities. It is as if we are not passive observers of the universe, but active participants in its unfolding. The Copenhagen interpretation embraced the probabilistic nature of quantum mechanics not as a flaw, but as a fundamental truth. This was a stark departure from classical physics, where determinism reigned supreme, where knowing the initial conditions of a system allowed you to predict its future with certainty. In the quantum world, however, certainty was an illusion. All we can ever hope to know are probabilities, the likelihood of finding a particle in a particular state. Bohr famously used the concept of complementarity to address the apparent paradoxes of quantum mechanics, like wave-particle duality. He argued that wave and particle descriptions were not contradictory, but rather complementary aspects of reality. They were two sides of the same coin, each providing a partial but essential understanding of the quantum world. It was like looking at a statue from different angles, each perspective revealing different features. The debate between Bohr and Einstein was not just about physics, it was about philosophy, about the very nature of reality itself. Einstein clung to the idea of an objective reality, existing independently of observation, a reality that could be described with certainty. Bohr, on the other hand, embraced the subjective role of the observer, the inherent uncertainty of the quantum world, and the idea that reality is, in some sense, created by our act of observing it. Think of it as a painter arguing with a photographer. The painter believes in capturing the essence of a subject through interpretation and artistic license, while the photographer insists on the objective truth of the image captured by the lens. Both are valid representations, but they offer fundamentally different perspectives. The stakes were incredibly high. If Einstein was right, quantum mechanics was incomplete, and a deeper, more deterministic theory was waiting to be discovered. If Bohr was right, then the universe was fundamentally probabilistic, and our classical intuitions about reality were simply wrong. This wasn't just an academic squabble. It was a battle for the very definition of what science could tell us about the world. The echo of this intellectual clash still reverberates through the halls of science to this day. This intellectual feud wasn't a battle of right versus wrong, but a wrestling match between two fundamental visions of the cosmos. Where did the truth truly lie? The answer, as it turns out, might just be even stranger than either man imagined. The stage is set. The titans have clashed. But amidst the swirling intellectual dust of the Einstein-Bohr debate, a fundamental question still hangs in the air. What is this entanglement? What is this cosmic connection that so deeply troubled Einstein? Forget magnets snapping together or radio waves invisibly linking our phones. This is something far more fundamental, a connection woven into the very fabric of reality. Imagine a pair of gloves. Not just any gloves, but quantum gloves. The instant you see one is a left-hand glove, without looking, the other is a right-hand glove, no matter how far apart they are. Entanglement takes that simple connection and cranks it up to 11, infusing it with the bizarreness only quantum mechanics can provide. Instead of gloves, think of two subatomic particles, perhaps two photons of light, created together in a specific way. These particles become intrinsically linked, their fates intertwined in a way that defies classical intuition. This linkage is called quantum entanglement. These particles are connected in such a way that they share the same fate. Imagine Alice is on Earth and Bob is on Mars. They each have one of these entangled photons. The photons each possess a property we will call spin, which can be either up or down. Until a measurement is made, each photon exists in a superposition, meaning it is simultaneously spinning both up and down, a fuzzy, undefined state of potential. Now here's where the magic happens. Alice decides to measure the spin of her photon. Instantly, the superposition collapses and she finds that her photon is spinning up. Here is the really weird part. At that exact same moment, the superposition of Bob's photon also collapses, and he finds his photon is spinning down, even though it is millions of miles away on Mars. It is as if the two photons are communicating instantaneously, coordinating their spins faster than light could possibly travel between them. This is the spooky action at a distance that so bothered Einstein. The particles are not physically connected by any wire or signal. The connection is intrinsic, a part of their quantum nature. The measurement on one instantaneously influences the state of the other. It is as if you and a friend each have a coin hidden in your hand. You agree that one of you will definitely have heads and the other will have tails. There is no way of knowing which of you has which until you reveal them. Even if you go to opposite sides of the earth, the instant you open your hand and see heads, you know your friend has tails, even if they have not opened their hand yet. Entanglement, though, takes this a step further. Until you open your hand, it is as if the coin is in both states, heads and tails, simultaneously, until you look. This instant influence is key. The distance between the particles doesn't matter. Whether they are an inch apart or on opposite sides of the galaxy, The correlation remains. It is a connection that seems to transcend space itself. This isn't about sending a signal. It is about the fundamental interconnectedness of the universe at the quantum level. It's like two dancers perfectly mirroring each other's movements, even when they can't see each other. The implications are staggering. It challenges our most basic assumptions about reality, about locality, about cause and effect. But is it all just theoretical mumbo-jumbo, or can this connection be harnessed, controlled, and used? Can we forge these links and make them dance to our tune? The answer, as we will soon see, will change everything. So we've established that this entanglement thing is real. It's not just some theoretical daydream cooked up in a physics lab. But if it's so bizarre, so counterintuitive, how do scientists even make it? It's not like you can just stumble across entangled particles lying around. These quantum connections are not something that typically happens spontaneously in easily observable ways. It is an orchestrated dance, a delicate ballet performed with lasers, crystals, and a whole lot of ingenuity. Physicists are, in essence, coaxing nature into revealing its strangest correlations. Think of it like this. Entanglement isn't a natural resource. It's a manufactured product. It is like forging steel or brewing beer. It requires specific ingredients, precise conditions, and a touch of alchemical skill. And the results, like a perfectly crafted sword or a well-aged ale, can be truly extraordinary. One of the most common methods for creating entangled photons is a process called spontaneous parametric down conversion. Sounds complicated, right? Well, the basic idea is surprisingly elegant. Imagine shining a powerful laser beam, not just any laser beam, but one carefully tuned to a specific frequency, onto a special kind of crystal. This crystal, often made of a material called beta barium borate, or something equally exotic, acts as a kind of quantum transformer. What happens next is nothing short of remarkable. Occasionally, a single photon from the laser beam will spontaneously split into two new photons inside the crystal. These new photons are not just any photons, they are entangled. They are born together, linked at the hip, sharing a quantum destiny. These newborn photons have correlated properties. For example, they might have opposite polarizations, meaning if one is vertically polarized, the other will be horizontally polarized. Remember those quantum gloves? These are quantum photons, and they know which way their partner is oriented instantly. The setup itself is a marvel of precision engineering. Everything has to be just right. The laser needs to be perfectly aligned, the crystal needs to be precisely cut, and the entire experiment needs to be shielded from stray light and vibrations. Even the slightest disturbance can disrupt the delicate quantum dance and destroy the entanglement. It is like trying to build a house of cards in the middle of a hurricane. Every precaution is vital, but creating the entanglement is only half the battle. Scientists also need to verify that the entanglement is actually there. This involves carefully measuring the properties of the entangled photons and checking for correlations. This is where things get really tricky. The measurements themselves need to be performed with extreme precision, using sophisticated detectors and complex data analysis techniques. There are other methods for creating entanglement, too. Scientists can entangle atoms by trapping them in place with lasers and then manipulating their internal energy levels. They can even entangle electrons by carefully controlling their interactions in specialized materials. The specific method depends on the type of particles being entangled and the desired properties of the entangled state. These experimental setups are not just sterile laboratory environments. They are the birthplaces of quantum technologies. Here, the seemingly impossible is made possible. They are temples of innovation, where scientists are pushing the boundaries of human knowledge and paving the way for a future powered by quantum mechanics. But the question lingers. What does it mean to control this quantum phenomenon? What secrets will this unlocking unveil? We have coaxed nature into revealing its strangest correlations, but now we stumble upon perhaps the most perplexing part of entanglement, the seemingly instantaneous connection between particles separated by vast distances. Forget the limitations of radio waves or even the fastest rocket ever built. We are talking about correlations that appear to transcend the very fabric of space-time, a connection that Einstein himself famously dubbed spooky action at a distance. But what does this instantaneous effect truly mean? And is it really as spooky as it sounds? Imagine Alice and Bob, our intrepid quantum explorers, each holding one of these entangled photons we created earlier. Alice, back in her lab on Earth, decides to measure the polarization of her photon. She performs her experiment, and instantly she knows the polarization of Bob's photon on Mars, even before any light signal could have possibly traveled between them. It's like flipping a switch here and having a light bulb illuminate instantaneously on the other side of the universe. This instantaneous correlation is the heart of entanglement's mystery. It suggests that the two particles are somehow connected by something beyond our normal understanding of space and time. It appears to violate the cosmic speed limit, the ultimate law of physics dictated by Einstein's theory of relativity, which states that nothing can travel faster than light. This speed limit is a cornerstone of modern physics. It underlies our understanding of gravity, electromagnetism, and pretty much every other force in the universe. So how can entanglement seemingly circumvent this fundamental law? The key word here is seemingly. The measurement of one entangled particle instantaneously determines the state of its partner, but what does that actually mean? It's crucial to understand that this instantaneous correlation does not allow for faster-than-light communication. Alice cannot use her measurement to send a predetermined message to Bob on Mars. Why not? Because the outcome of her measurement is inherently random. She can choose to measure the polarization along different axes, but the result she gets will always be random. It is like flipping a coin. You know instantly what the other person's coin landed on. But you can't control what side the coin will land on. Bob, on Mars, will see a random sequence of polarization results. Only when Alice sends him her measurement results via a classical communication channel, say radio waves traveling at the speed of light, can they compare their data and see the correlations. It's like Alice mailing Bob a record of all her coin flips, then Bob looking at his own record and seeing the perfect anti-correlation. This distinction between correlation and communication is absolutely crucial. Entanglement allows for instantaneous correlation, but it does not allow for the transmission of controllable information faster than light. In a way, entanglement is more like a pre-arranged agreement. Imagine Alice and Bob agree that one will flip heads and the other tails. This doesn't make the instantaneous effect any less mind-boggling. It simply means that it cannot be used to send signals faster than light. The spooky action at a distance is real, but it's a correlation, not a cause. It's a deep interconnectedness that challenges our intuitive understanding of cause and effect. It forces us to grapple with the question of what it truly means for two particles to be separate when they are linked by this fundamental quantum connection. This has fueled countless debates among physicists, philosophers, and even science fiction writers, each trying to unravel the true meaning of this bizarre quantum phenomenon. The ramifications of entanglement, while not breaking the laws of physics, challenge what it means to influence something far away. It's a phenomenon that continues to inspire wonder and to redefine the very foundations of our understanding of reality. But where do we go from here? We have witnessed the bizarre dance of entangled particles, seemingly defying the very laws of physics. But how do you prove something that sounds like magic? How do you put Einstein's spooky action at a distance to the ultimate test? For decades, the EPR paradox remained a philosophical curiosity, a thought experiment debated in ivory towers. Then, in 1964, a brilliant physicist named John Bell dared to ask a question that would change everything. Bell was not satisfied with mere philosophical arguments. He wanted empirical evidence, a way to definitively determine whether Einstein's hidden variables were real or whether quantum mechanics truly held the key to understanding reality. He sought to transform the esoteric debate into something that could be tested in a laboratory. Bell's theorem is the theoretical framework he devised. Bell, a modest and unassuming Northern Irishman working at CERN, the European Organization for Nuclear Research in Switzerland, found himself wrestling with the implications of the EPR paradox. While not as publicly renowned as Einstein or Bohr, Bell possessed a razor-sharp intellect and a deep understanding of quantum mechanics. He felt compelled to address the fundamental question at the heart of the debate. Was quantum mechanics truly complete? Or was there a deeper, hidden reality waiting to be uncovered? Bell's genius lay in his ability to translate a philosophical debate into a concrete mathematical framework. He realized that if Einstein's hidden variables were real, they would impose certain constraints on the correlations observed between entangled particles. He was able to translate those constraints into mathematical inequalities. These inequalities, now known as Bell's inequalities, provided a clear and unambiguous test. Any theory based on local realism, the idea that objects have definite properties independent of measurement and are only influenced by their immediate surroundings, must satisfy these inequalities. If experiments showed results that violated Bell's inequalities, it would be a death blow to Einstein's preferred explanation and a resounding victory for quantum mechanics. Think of it like this. Imagine you have a deck of cards. If the cards are shuffled randomly, certain statistical patterns will emerge. But if the cards are prearranged in a specific order, those patterns will be different. Bell's inequalities were like those statistical patterns, a way to distinguish between a universe governed by randomness and one governed by hidden variables. Bell's theorem was a monumental achievement, a theoretical tour de force that transformed the landscape of quantum mechanics. It provided a roadmap for experimentalists, a way to finally settle the debate between Einstein and Bohr, a way to determine whether the universe was truly as strange as quantum mechanics suggested. But the question remained, could experiments be designed to actually test Bell's inequalities? Could scientists actually put spookiness itself to the ultimate proof? Bell's theorem, a gauntlet thrown, a challenge issued. But theorems, however brilliant, are just words on paper, mathematical frameworks waiting to be tested by the unforgiving hand of reality. Could anyone actually design an experiment capable of probing the deepest mysteries of entanglement, of finally settling the score between Einstein and Bohr? The answer, as it often does in the world of scientific breakthroughs, came from a place of relentless curiosity and painstaking attention to detail. Enter Alain Aspect, a French physicist who, in the early 1980s, embarked on a series of experiments that would forever change our understanding of quantum mechanics. Aspect wasn't just testing Bell's theorem, he was putting the very nature of reality on trial. Aspect's experiments were not simple affairs. They were intricate, complex, and required a level of precision that pushed the boundaries of existing technology. Imagine a laboratory filled with lasers, mirrors, lenses, and detectors, all meticulously aligned and calibrated. It was a symphony of light and optics orchestrated to reveal the hidden secrets of the quantum world. At the heart of Aspect's setup was a source of entangled photons similar to the one we described earlier, but Aspect went a step further. He needed to ensure that the measurements on the entangled photons were performed quickly, before any possible communication could occur between them, even at the speed of light. To achieve this, he introduced a crucial element: rapidly switching detectors. Think of it like two archers aiming at targets. The archers need to randomly, independently, and rapidly switch between different target types as the arrows are released. Imagine one has a horizontal target and a vertical target. The other has a 45-degree target and a negative 45-degree target. The archers randomly switch. What the entanglement experiment does is see if the type of target each archer shoots at influences how well each archer does. Aspect's detectors were designed to randomly switch between different polarization angles at incredibly high speeds, faster than it would take light to travel from one detector to the other. This ensured that the measurement settings were truly independent, eliminating any possibility of hidden communication between the photons. It was a race against time, a quantum showdown where the fate of locality hung in the balance. The experiment was conducted with photons, tiny packets of light. Each photon was measured for polarization, its orientation of oscillation. The experiment measured correlations, how the polarization of one photon related to the polarization of its entangled twin. The results were clear, consistent, and unambiguous. Aspects experiments consistently violated Bell's inequalities. What did that mean? The correlations between the entangled photons were stronger than could be explained by any theory based on local realism. Einstein's hidden variables were ruled out. Quantum mechanics reigned supreme. Spooky action at a distance was not just a theoretical curiosity. It was a real, measurable phenomenon. Aspects experiments provided the strongest evidence to date that the universe is fundamentally non-local, meaning that events can be instantaneously correlated across space in ways that defy classical intuition. It wasn't just a victory for Bohr over Einstein. It was a victory for the weirdness of the quantum world, a confirmation that reality is far stranger and more interconnected than we could have ever imagined. These experiments weren't just about proving a point. They were about opening up a new realm of possibilities, a quantum frontier where the seemingly impossible becomes reality. But if the universe isn't local, and the laws of cause and effect are challenged, what does it mean for our understanding of reality? Aspects experiment had spoken. The universe wasn't just strange, it was undeniably non-local. But what does that really mean? It is not simply a question for physicists in lab coats, but one that strikes at the very heart of how we perceive reality. The experimental confirmation of Bell's inequality violation forces us to confront profound implications about the nature of existence itself. Suddenly, the familiar rules of cause and effect begin to blur. The intuitive idea that an object is only influenced by its immediate surroundings, that the universe is fundamentally local, is no longer a given. This challenges the very principle of local realism. It is the intuitive concept that objects possess definite properties regardless of whether they are being observed, and that these properties are only influenced by their immediate surroundings. Think of it like this. You believe your car is red whether you are looking at it or not, and its color can only be changed by things physically interacting with it like paint, not someone thinking about painting it blue. Imagine tossing a ball. In our everyday experience, we assume the ball has a definite trajectory, a predetermined path through space. We believe it had that path whether we watch it fly or not. But in a non-local universe, the ball's trajectory might not be so definite until we actually observe it. Its path might be influenced by something happening far away, something seemingly unrelated. Does that sound like science fiction? Perhaps. But that is the kind of mind-bending possibilities that entanglement forces us to consider. Suddenly, we are confronted with the unsettling possibility that reality only becomes definite upon measurement. Before we observe something, is it merely a haze of possibilities, a superposition of states, Does our active observation somehow collapse this superposition, forcing the universe to choose a single reality? It is as if the universe is waiting for us to look before deciding what it is. It's a bit like the old philosophical question. If a tree falls in a forest and no one is around to hear it, does it make a sound? Entanglement takes that question and cranks it up to 11. It asks, if a particle has a property like spin but no one measures it, does that property actually exist? Or is it only created in the act of measurement? This challenges our deep-seated belief in an objective reality, a reality that exists independently of our perception. It challenges the idea that the universe is a clockwork mechanism ticking away according to predetermined laws. Instead, it suggests that reality is, in some sense, participatory, that our consciousness plays a role in shaping the world around us. This is not to say that we can will things into existence. That is a step too far. But it does suggest that the act of observation is not a passive one, but an active interaction with reality. Think of it like a canvas. Before the artist begins to paint, the canvas is a blank slate full of potential. The artist's brush strokes bring the painting into being, shaping the colors and forms, creating a unique and individual work of art. In a similar way, our observations might be like brush strokes on the canvas of reality, shaping the quantum possibilities into the definite world we experience. This does not mean that the universe is all in our head. There are still objective laws of physics that govern the behavior of matter and energy. But it does mean that our relationship with reality might be more intimate, more interconnected than we ever imagined. This non-locality, this apparent violation of cause and effect, raises profound questions about the nature of time itself. If two particles can be instantaneously correlated across vast distances, does that mean that time is not as fundamental as we thought? Does it mean that the past, present, and future are somehow intertwined in a way that we do not yet understand? Perhaps the universe is not a linear progression of events, but a vast, interconnected web where everything is linked to everything else. It is akin to taking the concept of 6 degrees of separation from sociology to physics. These are not easy questions to answer. They push us to the very limits of our understanding. But it is precisely in these moments of uncertainty, in these challenges to our most basic assumptions, that scientific progress is made. It is in grappling with the weirdness of entanglement that we begin to glimpse a deeper, more profound understanding of the universe and our place within it. The implications are earth-shattering. But can we actually use this spooky connection to send a message faster than light? So we find ourselves at a fascinating crossroads. We have witnessed the seemingly impossible. Particles linked across vast distances, their fates intertwined in a dance that transcends space and time. But does this cosmic connection hold the key to unlocking the ultimate dream? Instantaneous communication, messages flashing across the universe faster than light itself? The short answer, perhaps surprisingly, is no. It is a tantalizing prospect. Imagine a future where news travels not at the speed of light, but instantaneously, where we could communicate with distant stars in the blink of an eye, where the limitations of distance become irrelevant. But entanglement, despite its apparent defiance of the laws of physics, does not provide a shortcut around the cosmic speed limit. It is a subtle, yet crucial distinction, a difference between correlation and control, between shared fate and deliberate messaging. Think of it like this. Imagine you and a friend are each given a sealed envelope. You are told that one envelope contains a red card and the other contains a blue card, but you don't know which is which. You and your friend then travel to opposite sides of the planet. When you open your envelope, you instantly know the color of the card your friend holds, even before they open their envelope. This is a perfect correlation, but it doesn't allow you to send a message. You can't choose the color of your card, and you can't control what your friend will find in their envelope. Entanglement is similar. When Alice measures the state of her entangled particle, she instantly knows the state of Bob's particle, but she cannot control the outcome of her measurement. The result is inherently random. It is governed by the probabilistic nature of quantum mechanics. She may choose what property to measure, such as polarization or spin, but whatever her selection, her result will remain indeterminate until the moment of measurement, making it useless for the transmission of any intentional signal. Bob, on the receiving end, will simply see a random series of measurements, a jumble of ups and downs, lefts and rights, with no discernible pattern. He cannot tell whether Alice is trying to send him a message or simply performing random measurements. Only when Alice and Bob compare their results via a classical communication channel, say a phone call or an email, can they see the correlations. They can then confirm that their measurements are indeed perfectly correlated, but this communication will happen at the speed of light. It is like having two dice that are magically linked. Whenever you roll your die, you instantly know what number your friend rolled, even if they are light years away. But you cannot use this connection to send a message because you cannot control what number you will roll. The outcome is always random. So, while entanglement is undeniably spooky and challenges our intuitive understanding of reality, it does not violate the fundamental laws of physics. It does not allow for faster-than-light communication. It is a correlation, not a cause. A shared fate, not a controllable signal. It seems that Einstein's speed limit remains secure, but does that mean that entanglement is useless? Is it merely a philosophical curiosity, a bizarre quantum phenomenon with no practical applications? Far from it. As we will soon see, entanglement is a powerful resource, a key ingredient in a new generation of technologies that promise to revolutionize computation, communication, and sensing. The limitations on using entanglement for sending signals faster than light may seem like a roadblock, but this restriction has opened doors to equally extraordinary possibilities in the quantum world. What possibilities might those be? But if entanglement can't be used for sending a message faster than light, what's really going on when we measure these entangled particles? How can information about one particle's state appear to be instantaneously reflected in its partner without any signal being sent? Is it some kind of cosmic illusion, a quantum parlor trick that fools us into thinking information is being transferred when it really isn't? Prepare to delve into one of the most subtle and fascinating aspects of entanglement, the dance of information where correlation reigns supreme but causation takes a back seat. It's a question that has puzzled physicists for decades. How can two particles, separated by vast distances, seem to know about each other's state instantaneously? It is not as simple as saying they are exchanging signals at speeds exceeding that of light. Instead, it's as if they're participating in a shared, predetermined event, like two actors reading from the same script, only the script is written in the language of quantum mechanics. The key lies in understanding the concepts of shared randomness and the inherent uncertainty that governs the quantum world. Think of it as two lottery tickets being printed at the same time. Each ticket contains a series of numbers, and the numbers on one ticket are perfectly correlated with the numbers on the other. However, until the winning numbers are drawn, neither ticket has any intrinsic value. The numbers are simply random symbols. It is only when the winning numbers are announced that the value of the tickets is determined. This is akin to entangled particles and how they reveal quantum information. Entangled particles are born into a state of shared destiny. They possess correlated properties from the moment of their creation. But these properties remain undefined in a superposition of possibilities until a measurement is made. When Alice measures her particle, she is not sending any information to Bob's particle. Instead, she is collapsing the superposition, forcing both particles to choose a definite state. It's like two sides of the same coin spinning in the air. Until the coin lands, both sides are equally possible. However, the moment the coin lands, both sides are determined simultaneously. The outcome is random, but the correlation is perfect. This inherent randomness is crucial because it is the very thing that prevents us from using entanglement for faster-than-light communication. While entanglement allows for the instantaneous correlation of properties, it does not allow for the instantaneous transfer of controllable information. The result of any single measurement on one particle is inherently random. You can't control which face of the quantum coin appears, and it is this randomness that prevents any causal signaling. Consider a pair of perfectly synchronized clocks. Both clocks will always show the same time no matter how far apart they are. However, simply observing one clock does not transmit any information to the other clock. The time is merely a correlation. Imagine you have a pair of gloves, one left and one right. You place each glove in a box and give one box to an astronaut on a mission to Mars. Until the astronaut opens the box, it's not possible to know which glove is in which box. However, the moment they open the box and see a left-handed glove, they instantly know, without any signal being sent, that their colleague on Earth has the right-handed glove. This may sound counterintuitive, but entanglement provides a nuanced view of information transfer. It shows us that correlation does not necessarily imply causation, and that quantum information operates under very different rules than classical information. It is a dance of randomness and interconnectedness, where the very fabric of reality is woven together in ways that continue to challenge our understanding of the universe. But what implications does all this have for our understanding of time? Could entanglement be hinting at a deeper relationship between information, space, and the very flow of time itself? It remains one of the great unanswered questions in quantum physics. It's a mystery that continues to beckon researchers into the strange and wonderful world of quantum entanglement. It's a place where the very notion of information is being redefined. And what happens when these strange quantum links aren't limited to tiny particles but extend to objects we can see and touch? So we've established that quantum entanglement is not merely theoretical, but a real and measurable phenomenon, a correlation that defies our classical understanding of space and time. But what if this spooky action wasn't confined to the realm of photons and electrons? What if we could entangle bigger things, things we can actually see and touch? Is it even possible to bridge the gap between the quantum world of the incredibly small and the classical world of our everyday experience? For years, entanglement was thought to be the exclusive domain of fundamental particles, those tiny building blocks of matter that dance according to the bizarre rules of quantum mechanics. But scientists, driven by an insatiable curiosity and a relentless pursuit of knowledge, have been pushing the boundaries of what is possible, venturing into uncharted territory where the quantum and classical worlds collide. And what they have discovered is nothing short of astonishing. Imagine, if you will, not just two photons linked together, but two entire atoms, those indivisible units of matter that make up everything around us, sharing a quantum destiny. Scientists have successfully entangled atoms, trapping them in place with lasers and manipulating their internal energy levels to create these quantum connections. These experiments are not easy. They require extreme precision and control, but the results are undeniable. We are stretching the realm where entanglement can be observed, but the ambition doesn't stop there. Researchers are pushing even further, attempting to entangle molecules, those complex structures made up of multiple atoms bonded together. Think of molecules like tiny Lego creations. Successfully entangling them would be a remarkable feat, pushing the boundaries of our understanding of quantum mechanics and paving the way for new technologies. After all, chemistry is nothing more than the interactions between molecules. What new potential does entanglement offer us in manipulating them? And what about macroscopic objects, things that are visible to the naked eye? Could we ever entangle something big, something tangible, something that defies our classical intuitions about reality? As absurd as it sounds, scientists are making progress in this direction. In one groundbreaking experiment, researchers managed to entangle two tiny vibrating membranes, each about the size of a human hair. These membranes were cooled to near absolute zero, the lowest temperature possible, to minimize thermal vibrations and isolate the quantum effects. The result? Two macroscopic objects vibrating in perfect synchrony, linked by the mysterious force of quantum entanglement. These advancements are not just about breaking records or achieving scientific milestones. They are about fundamentally changing our understanding of the universe and unlocking new technological possibilities. Entangling bigger things could lead to more powerful quantum computers, more sensitive quantum sensors, and more secure quantum communication networks. It is about harnessing the power of entanglement to create a future that was once thought to be impossible. These experiments are pushing the boundaries between the quantum and classical worlds, forcing us to rethink our understanding of reality. They challenge our deeply held beliefs about locality, causality, and the nature of measurement. If we can entangle macroscopic objects, Does that mean that the entire universe is fundamentally interconnected, a vast web of quantum entanglement where everything is linked to everything else? It is a question that continues to inspire wonder and to drive scientific exploration. And what new potential does it offer in testing new theories of quantum gravity? Where does this path lead us? We are reaching the point where quantum links span objects within our grasp. But if the universe is so deeply connected, could we potentially transport something? The idea of teleportation has long captured the imagination, fueling countless science fiction stories, from Star Trek's transporter rooms to the fantastical apparitions in Harry Potter. Is it possible to somehow dematerialize an object in one location and instantly reconstruct it somewhere else? The reality of quantum teleportation, while still mind-bending, is a bit more nuanced than its science fiction counterpart. Prepare to have your conceptions challenged. The term quantum teleportation evokes images of beaming people across vast distances. However, quantum teleportation does not involve transporting matter in the traditional sense. It's not about dismantling an object and reassembling its atoms somewhere else. Instead, it's about transferring the quantum state of one particle onto another distant particle. It's like copying and pasting information, but instead of digital bits, it's quantum information. Imagine you have a rare and fragile antique vase. Instead of physically shipping it across the country, with all the risks of damage or loss, you could instead create a perfect replica at its destination. You would need to carefully analyze every detail of the original vase, its shape, its color, its composition, and then transmit that information to the other location, where a skilled artisan could use it to create an exact copy. Quantum teleportation is similar, but instead of copying the classical properties of a vase, it copies the quantum properties of a particle. This quantum state contains all the information about a particle, its spin, its polarization, its energy levels, everything that defines its quantum identity. Quantum teleportation transfers this information from one particle, the sender, often called Alice, to another particle, the receiver, often called Bob, even if they are separated by vast distances. In fact, it is not even the information itself that is teleported, but the quantum state. The original state disappears from Alice's particle and reappears on Bob's, while Alice's particle takes on a new, meaningless state. Now here's where entanglement comes in. Quantum teleportation wouldn't be possible without entanglement as one of its essential resources. Alice and Bob must share a pair of entangled particles. Remember those entangled photons from previous chapters, the ones whose fates are intertwined regardless of the distance separating them? These entangled particles serve as a quantum communication channel between Alice and Bob. One entangled particle is given to Alice and the other is given to Bob. Here's the tricky part. To teleport the quantum state of a third particle, let's call it particle 1, Alice needs to perform a special measurement on particle 1 and her entangled particle, particle 2. This measurement is called a Bell measurement, and it entangles particle 1 and particle 2 in a specific way. The result of this measurement is a set of classical data, a series of bits that describe the outcome of the measurement. This data has to be sent to Bob via a classical communication channel like a telephone line or an email. This classical communication channel is another crucial component of quantum teleportation. Without it, the process cannot be completed. Bob uses the classical data he receives from Alice to perform a specific operation on his entangled particle, particle 3. This operation transforms particle 3 into a perfect replica of particle 1. In other words, the quantum state of particle 1 has been successfully teleported to particle 3. It's important to emphasize that the original quantum state of particle 1 has been destroyed in the process. Quantum teleportation doesn't create a copy. It transfers the original state. It's like photocopying something. While the photocopy now contains the same information as the original cannot be used again because it has been used to create the copy. It is also worth noting that the signal must be transmitted through a classical channel which means it can never be faster than light. What makes quantum teleportation so extraordinary? It allows us to transfer quantum information without physically moving the particle that carries it. This has profound implications for quantum computing and quantum communication. Imagine a future where quantum computers are connected by a quantum internet, allowing them to share quantum information securely and instantaneously. Quantum teleportation would be a key technology for enabling such a network. It could also be used to transfer quantum information within a quantum computer, allowing for more complex and powerful calculations. While the reality of quantum teleportation may not involve beaming people across space, it is a revolutionary technology that is poised to transform our understanding of information and communication. Quantum networks may use entanglement and teleportation in the near future. It represents a significant step towards a future where the seemingly impossible becomes reality. But what are the building blocks of these future quantum networks, and how can teleportation help connect them? So the promise of quantum teleportation shimmers on the horizon, hinting at a future where information can be moved without physically moving the messenger. But even more profound is the revolution brewing within the silicon heart of computation itself. What if we could harness the very spookiness of entanglement not just to send information, but to fundamentally change how we process it? Imagine a computer capable of calculations that would take even the most powerful supercomputers millennia to complete. This isn't science fiction, it's the promise of the quantum computer, and entanglement is one of its essential power sources. Classical computers, the devices that power our modern world, store information as bits, representing either a 0 or a 1. Think of it as a light switch, either on or off, black or white, a binary world of limited possibilities. Quantum computers, however, operate on a completely different principle, leveraging the mind-bending concepts of superposition and entanglement to create quantum bits, or qubits. These qubits aren't limited to representing just 0 or 1. They can exist in a superposition of both states simultaneously. It is like that coin we discussed earlier, spinning in the air, existing as both heads and tails at the same time until it lands. A qubit can be 0, 1, or a combination of both, offering a vastly richer landscape of possibilities. But superposition is only part of the story. The real magic happens when we entangle multiple qubits. When qubits become entangled, they share a combined quantum state, a single, interconnected entity, regardless of the physical distance separating them. It's like having a team of musicians, each capable of playing multiple notes at once. But instead of playing their notes independently, they are perfectly synchronized, their instruments vibrating in harmony, creating a complex and beautiful symphony. Entangled qubits work in a similar way, existing in a shared state that allows for massive parallelism in computation. While a classical computer processes information sequentially, one bit at a time, a quantum computer can perform calculations on all possible states of its entangled qubits simultaneously. This exponential increase in computational power is what makes quantum computers so revolutionary. Imagine trying to find a single grain of sand on a beach. A classical computer would have to examine each grain of sand individually, a tedious and time-consuming process. A quantum computer, however, could examine all the grains of sand simultaneously, instantly identifying the one you are looking for. This is the power of quantum parallelism, and it is entanglement that makes it possible. Certain complex problems are simply intractable for classical computers. Think of simulating the behavior of molecules to discover new drugs, optimizing complex logistical networks to improve efficiency, or breaking the most sophisticated encryption codes to protect sensitive data. These are the kinds of problems that quantum computers are uniquely suited to solve. Entanglement acts as the linchpin, the central ingredient that unlocks this new realm of computational possibilities. It's the spooky connection that allows qubits to dance together, to explore possibilities far beyond the reach of their classical counterparts, forging a new era in computing. But just how much more powerful are these entangled qubits, and what other secrets do they hold? So the promise of quantum teleportation shimmers on the horizon, hinting at a future where information can be moved without physically moving the messenger. But even more profound is the revolution brewing within the silicon heart of computation itself. What if we could harness the very spookiness of entanglement, not just to send information, but to fundamentally change how we process it? Imagine a computer capable of calculations that would take even the most powerful supercomputers millennia to complete. This isn't science fiction. It's the promise of the quantum computer, and entanglement is one of its essential power sources. Classical computers, the devices that power our modern world, store information as bits representing either a 0 or a 1. Think of it as a light switch, either on or off, black or white, a binary world of limited possibilities. Quantum computers, however, operate on a completely different principle, leveraging the mind-bending concepts of superposition and entanglement to create quantum bits, or qubits. These qubits aren't limited to representing just 0 or 1. They can exist in a superposition of both states simultaneously. It is like that coin we discussed earlier, spinning in the air, existing as both heads and tails at the same time until it lands. A qubit can be 0, 1, or a combination of both, offering a vastly richer landscape of possibilities. But superposition is only part of the story. The real magic happens when we entangle multiple qubits. When qubits become entangled, they share a combined quantum state, a single interconnected entity, regardless of the physical distance separating them. It's like having a team of musicians, each capable of playing multiple notes at once. But instead of playing their notes independently, they are perfectly synchronized, their instruments vibrating in harmony, creating a complex and beautiful symphony. Entangled qubits work in a similar way, existing in a shared state that allows for massive parallelism in computation. While a classical computer processes information sequentially, one bit at a time, a quantum computer can perform calculations on all possible states of its entangled qubits simultaneously. This exponential increase in computational power is what makes quantum computers so revolutionary. Imagine trying to find a single grain of sand on a beach. A classical computer would have to examine each grain of sand individually, a tedious and time-consuming process. A quantum computer, however, could examine all the grains of sand simultaneously, instantly identifying the one you are looking for. This is the power of quantum parallelism, and it is entanglement that makes it possible. Certain complex problems are simply intractable for classical computers. Think of simulating the behavior of molecules to discover new drugs, optimizing complex logistical networks to improve efficiency, or breaking the most sophisticated encryption codes to protect sensitive data. These are the kinds of problems that quantum computers are uniquely suited to solve. Entanglement acts as the linchpin, the central ingredient that unlocks this new realm of computational possibilities. It's the spooky connection that allows qubits to dance together, to explore possibilities far beyond the reach of their classical counterparts, forging a new era in computing. But just how much more powerful are these entangled qubits, and what other secrets do they hold? Are we talking about a mere upgrade to existing technology, or a paradigm shift akin to moving from abacus to the digital age? The answer lies in understanding the fundamental unit of quantum information, the qubit, and how entanglement dramatically amplifies its inherent power. Classical bits, the workhorses of our everyday computers, are binary, existing in a state of either 0 or 1. Think of it as a light switch, either on or off, a simple choice, but a limitation nonetheless. Qubits, on the other hand, shatter this limitation, existing in a superposition, simultaneously embodying 0 and 1. This is where things get truly mind-bending. Imagine a famous painting by Salvador Dali, The Persistence of Memory, with its melting clocks draped over surreal landscapes. Now picture each clock representing a bit of information. In a classical computer, each clock could only display one time at any given moment.
A qubit, however, is like a clock that displays every possible time simultaneously, existing in a blurry, undefined state until observed. This superposition allows a single qubit to explore a multitude of possibilities, a feat impossible for its classical counterpart. But the true power of the qubit is unleashed when we entangle it with others. Unlike classical bits that operate independently, entangled qubits become intrinsically linked, their fates intertwined in a way that defies classical intuition. It's as if each clock in our Dali painting suddenly became connected, their hands moving in perfect synchronicity, influencing each other across the canvas. Think of it like a chorus of voices, each capable of singing a wide range of notes. When they sing independently, the sound is chaotic and unstructured, but when they harmonize, their voices blend together to create something far more beautiful and complex. Entanglement is the quantum harmony that allows qubits to work together to explore far more possibilities at once than they could individually. Entangled qubits offer a vast increase in computing power compared to classical bits. With 2 classical bits, you can represent 4 possible states: 0, 0, 0, 1, 1, 0, and 1, 1. With 2 entangled qubits, you can represent all 4 states simultaneously, exponentially increasing the computational possibilities. The number of possible states grows exponentially with each added qubit. 30 entangled qubits can represent more than 1 billion states simultaneously, dwarfing the capabilities of even the most powerful supercomputers. This synergy between superposition and entanglement is the very heart of quantum advantage, the ability of quantum computers to solve problems that are simply impossible for classical machines. It is the key to unlocking new frontiers in medicine, materials science, artificial intelligence, and countless other fields. But the real challenge lies in maintaining these fragile quantum states, in shielding them from the outside world, and harnessing their power to perform meaningful computations. What might the future hold when we fully master this dance of entangled qubits? And can we truly unleash the potential of a quantum world? But what if instead of faster-than-light messages, we could use entanglement to create something even more valuable, an unbreakable code? In a world increasingly reliant on digital communication, where sensitive information flows across networks at the speed of light, the threat of cyber attacks looms large. From state secrets to personal financial data, everything is vulnerable to prying eyes. But what if there was a way to guarantee absolute security? A way to shield our communications from even the most sophisticated eavesdroppers? Enter quantum cryptography, the art of using the laws of quantum mechanics to protect information, and at its heart lies entanglement. Imagine Alice and Bob, 2 individuals who need to exchange a secret message. Forget complex algorithms and long passwords. Instead, they turn to the quantum realm. Alice and Bob begin by sharing a series of entangled particles, created with the precision and care we discussed earlier. Each particle is carefully sent to Alice or Bob to perform their task. Thanks to the strangeness of quantum physics, if anyone attempts to intercept these particles or measure their properties, the entanglement is immediately disturbed, alerting Alice and Bob to the presence of an eavesdropper. It's like having a built-in alarm system that detects any intrusion. This is the foundation of quantum key distribution, or QKD, a revolutionary approach to secure communication. With QKD, Alice and Bob can use their entangled particles to generate a secret encryption key, a random string of numbers that can be used to encrypt and decrypt their messages. The beauty of this approach is that the security of the key is guaranteed by the laws of quantum mechanics. Any attempt to eavesdrop on the key generation process will inevitably leave a trace, alerting Alice and Bob to the presence of an attacker. Consider a classic spy scenario, where Eve, the cunning eavesdropper, is trying to steal the secret message between Alice and Bob. In traditional cryptography, Eve might try to crack the code by using powerful computers or sophisticated algorithms. But with quantum cryptography, Eve faces a much greater challenge.
Any attempt to intercept the entangled particles will inevitably disturb their quantum state, leaving a telltale sign that Alice and Bob can detect. It's like trying to steal a priceless painting. Any attempt to touch or move the painting will set off an alarm, alerting the authorities. Imagine Alice sends Bob a series of entangled photons. Eve, lurking in the shadows, tries to intercept these photons to learn the secret key. But the moment Eve tries to measure the polarization of a photon, she disturbs its quantum state, introducing errors into the key generation process. Alice and Bob can then compare a portion of their keys publicly. If their results are dissimilar, they will know an interception has occurred. If they match, they can use their newfound secret key to transmit the message. This inherent security is what makes quantum cryptography so promising. It is not based on the complexity of mathematical algorithms, which can be broken with enough computing power. Instead, it is based on the fundamental laws of physics, which cannot be circumvented. The universe itself guarantees the security of the key. This is in stark contrast to traditional cryptography, which relies on the assumption that the attacker doesn't have enough computing power to break the code. With the rise of quantum computers, this assumption is becoming increasingly questionable. Quantum computers have the potential to break many of the encryption algorithms that we rely on today, leaving our digital communications vulnerable. Quantum cryptography offers a solution to this looming threat, providing a future-proof way to secure our information. Is this the end of the code-breaking game? Maybe it is, maybe it isn't. The field of quantum cryptography is rapidly evolving, with new protocols and techniques being developed all the time. But one thing is certain. Entanglement is at the heart of this revolution, providing a foundation for secure communication that is unlike anything we have ever seen before. If we could use entanglement to enhance other quantum systems, like sensors, what might we be able to detect that has eluded us before? We've unlocked the potential for unbreakable codes. But what if we could use quantum entanglement to build something even more astonishing? Sensors with sensitivity so profound, they would redefine the limits of what we can detect. Forget conventional measurements shackled by the uncertainty principle. We're talking about a new era of precision, where the spooky connections of entanglement allow us to peer deeper into the fabric of reality. Imagine a world where doctors can diagnose diseases at their earliest stages with unprecedented accuracy, where navigators can pinpoint their location with pinpoint precision even in the absence of global positioning system, or global navigation satellite system, signals, and where scientists can finally detect the faintest whispers of gravitational waves, ripples in space-time caused by cataclysmic events billions of light-years away. It is not just a dream. It is the promise of quantum sensing. Classical sensors, the devices we use every day to measure temperature, pressure, light, and a myriad of other physical properties, are limited by the laws of physics. They are bound by what is known as the standard quantum limit, a fundamental barrier imposed by the uncertainty principle. The more accurately you try to measure one property, the less accurately you can measure another. It's like trying to take a picture with too high a resolution. The more you zoom in, the blurrier it becomes. But entanglement offers a way to circumvent this limit, to break through the noise and detect signals that would otherwise be lost in the quantum fog. By harnessing the unique correlations and sensitivity of entangled states, we can create quantum sensors that are far more precise than their classical counterparts. These sensors are essentially ultra-precise probes, capable of detecting the faintest disturbances in their environment. Consider medical imaging, the art of peering inside the human body to diagnose disease. Magnetic resonance imaging, or MRI, is a powerful tool, but it is limited by the sensitivity of its detectors. Quantum sensors utilizing entanglement could revolutionize MRI, allowing doctors to detect tumors at much earlier stages, potentially saving countless lives. Imagine an MRI scan so sensitive it could detect a single cancerous cell. Or imagine navigation systems so accurate they could guide ships and aircraft through the most challenging environments, even without global positioning system or global navigation satellite system signals. Quantum gyroscopes, using entangled atoms, could provide incredibly precise measurements of rotation, allowing for navigation that is immune to jamming or spoofing. Think of submarines navigating the depths of the ocean with unparalleled accuracy, or aircraft flying through turbulent weather with pinpoint precision. And what about the universe itself? Gravitational waves, ripples in space-time predicted by Albert Einstein over 100 years ago, are incredibly faint and difficult to detect. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, a massive scientific instrument designed to detect these waves, has revolutionized our understanding of the cosmos. Quantum sensors using entangled photons could further enhance the sensitivity of gravitational wave detectors, allowing us to probe the universe's most violent and mysterious events, from the collision of black holes to the birth of galaxies. Imagine peering back in time to the very beginning of the universe. These are not just hypothetical possibilities. Scientists around the world are actively working to develop and refine quantum sensors, pushing the boundaries of what is possible. They are creating entangled states of atoms, photons, and even macroscopic objects, all in the pursuit of creating sensors that are more sensitive, more accurate, and more versatile than anything we have ever seen before. It is an exciting time to be alive. A time when the bizarre and wonderful world of quantum mechanics is poised to transform our understanding of the universe and our ability to interact with it. But what exactly is it about entanglement that allows these sensors to achieve such ghostly precision, and what other secrets are waiting to be unveiled in this quantum realm? But what exactly is it about entanglement that allows these sensors to achieve such ghostly precision, and what other secrets are waiting to be unveiled in this quantum realm? What if the very fabric of reality, the way we measure time, space, and the fundamental forces of the universe, could be redefined, not by bigger machines, but by harnessing the power of spooky action? This is the promise of quantum metrology, the science of ultra-precise measurements using quantum effects like entanglement. Imagine peering into a world unseen, capturing images with resolution that shatters classical limits. This is not some fantastical vision. It is ghost imaging made possible by entangled photons. In classical imaging, you shine light on an object, and the light that bounces back is used to create an image. The resolution is limited by the wavelength of the light you are using, which means that to see smaller details, you need to use light with a shorter wavelength like ultraviolet or even X-rays. But these high-energy forms of light can be damaging to delicate samples, like biological cells. Ghost imaging offers a way around this limitation by using entangled photons. Here is how it works. You have a source that creates pairs of entangled photons. One photon in each pair is sent to interact with the object you want to image, but this photon never actually reaches a detector. The other photon, its entangled twin, is sent to a detector that never sees the object. Because the two photons are entangled, they share a perfect correlation. You can then use this correlation to reconstruct an image of the object, even though the detector never directly saw the object. It is like taking a picture of someone using only the shadow of their friend. But the magic of ghost imaging goes even further. Because the entangled photons share a quantum connection, the resolution of the image is not limited by the wavelength of the light that interacts with the object. Instead, it is limited by the wavelength of the light that reaches the detector. This means that you can use low-energy light to illuminate the object, minimizing damage, and still achieve high-resolution imaging. Think of the implications for medical diagnostics. Imagine being able to see the inner workings of a cell without damaging it, or detecting a tumor before it even forms. Ghost imaging could revolutionize the way we see the world, but the story doesn't end there. Entanglement is also revolutionizing the way we measure time. For centuries, humans have strived to create ever more accurate clocks, from the sundials of ancient Egypt to the atomic clocks of the modern era. Today, atomic clocks are the gold standard for timekeeping. They use the precise and predictable vibrations of atoms to measure time with incredible accuracy. These clocks are so accurate that they only lose about 1 second every several billion years. But even atomic clocks are limited by the laws of physics. The more accurately you try to measure the frequency of an atom's vibration, the longer you have to observe it. This is known as the standard quantum limit. But entanglement offers a way to break through this limit, to create atomic clocks that are even more accurate than what we thought was possible. Scientists are now building atomic clocks using entangled ions, charged atoms trapped in place by electric fields. By entangling these ions, they can create a collective quantum state that is far more sensitive to time than any individual atom. It is like having a chorus of singers, each singing a slightly different note. By listening to the chorus as a whole, you can hear subtle variations in pitch that would be impossible to detect in any individual voice. Atomic clocks based on entangled ions could achieve unparalleled accuracy, potentially improving timekeeping by orders of magnitude. Imagine the implications for global positioning systems or global navigation satellite systems, which rely on incredibly precise time measurements to determine location. More accurate clocks could lead to more accurate navigation, more precise financial transactions, and a deeper understanding of the fundamental laws of physics. But the potential applications of quantum metrology extend far beyond imaging and timekeeping. Entanglement can also be used to measure frequencies, magnetic fields, and other physical quantities with unprecedented precision. What about measuring the rotation of the Earth, or the subtle variations in gravity that reveal hidden deposits of oil and minerals? Imagine sensors so sensitive they could detect the faintest traces of explosives or toxins, protecting us from harm. Quantum metrology is not just about improving existing technologies, it's about creating entirely new ways of measuring the world, revealing details and insights that were previously hidden from view. It's about pushing the boundaries of human knowledge and unlocking the secrets of the universe. What if we could use these ultra-precise measurements to test the very foundations of physics, to search for new particles, new forces, and new dimensions? The possibilities are endless, the future uncertain, but one thing is clear: the quantum revolution is just beginning, and entanglement is leading the charge. Is this the next turning point? But now a question that has captivated scientists for decades rises. What if entanglement isn't just a laboratory curiosity, meticulously crafted within controlled environments? What if it exists naturally, on a cosmic scale, woven into the very fabric of the universe since its explosive birth? Could entanglement be the unseen hand connecting the furthest reaches of the cosmos, a ghostly echo of the Big Bang itself? Imagine for a moment the universe at its inception, a time of unimaginable density and heat, a singularity where all matter and energy were compressed into a volume smaller than an atom. In this primordial soup, particles would have been created in pairs, springing into existence together in an environment where quantum effects reigned supreme. Is it possible that these particles, born together in the crucible of creation, became entangled, their fates intertwined for all eternity? This is the tantalizing question at the heart of cosmic entanglement, a speculative but intriguing theory that suggests vast regions of the cosmos may be linked by ancient quantum connections. Forget the neatly arranged lasers and crystals of a physics lab. We are talking about a universe-spanning connection forged in the heart of the Big Bang, a connection that could potentially link galaxies, quasars, and even the most distant reaches of space-time. It's a mind-bending concept. Consider two photons created in the immediate aftermath of the Big Bang. They hurtle across the expanding universe, separated by billions of light years, their journeys seemingly independent. But according to the theory of cosmic entanglement, these photons remain intrinsically linked, their quantum properties correlated despite the vast gulf of space separating them. Measuring the polarization of one photon in a galaxy a billion light-years away would instantaneously determine the polarization of its entangled twin. even if that twin resides on the opposite side of the observable universe. This is not to suggest that entanglement is a force that can be harnessed to travel across the universe or transmit information faster than light. We already know that doesn't work. Instead, cosmic entanglement suggests a deeper, more fundamental interconnectedness, a blurring of the lines between cause and effect, between here and there, between then and now. It challenges our classical intuitions about the nature of space and time, hinting at a reality where the universe is not a collection of isolated objects but a vast interconnected web of quantum relationships. But how could we ever test such a theory? Measuring entanglement on such a vast scale seems almost impossible. The distances are so immense, the signals so faint, and the potential sources of interference so numerous that detecting these ancient quantum links would be like trying to hear a whisper across a roaring ocean. Currently, this remains firmly in the realm of theoretical speculation, but that hasn't stopped physicists from exploring the possibilities. Perhaps future generations of telescopes, equipped with quantum sensors capable of detecting the faintest traces of entanglement, will be able to probe the early universe, searching for the telltale signs of these primordial quantum connections. Or perhaps new theoretical breakthroughs will provide us with a deeper understanding of the relationship between quantum mechanics and gravity, allowing us to predict the existence and behavior of cosmic entanglement with greater certainty. The very idea that the entire universe might be bound together by ancient quantum links opens up a Pandora's box of possibilities. Could cosmic entanglement play a role in the structure and evolution of the universe? Could it explain the seemingly coordinated behavior of distant galaxies? Could it even provide a new perspective on the nature of dark matter and dark energy, those mysterious substances that make up the vast majority of the universe? Think about the implications. What if the universe isn't just expanding, but also subtly communicating with itself through this ancient network of entanglement? Is the entire universe, in some sense, one giant quantum system, its parts interconnected and interdependent in ways we are only beginning to understand? It's a breathtaking thought, one that challenges our very understanding of reality. What new perspectives will we discover? These questions lead us to another mind-bending theory. But now a question that has captivated scientists for decades rises. What if entanglement isn't just a laboratory curiosity, meticulously crafted within controlled environments? What if it exists naturally on a cosmic scale, woven into the very fabric of the universe since its explosive birth? Could entanglement be the unseen hand connecting the furthest reaches of the cosmos, a ghostly echo of the Big Bang itself? It is a breathtaking thought, one that challenges our very understanding of reality. What new perspectives will we discover? These questions lead us to another mind-bending theory, one that dares to connect the seemingly disparate worlds of quantum entanglement and the very geometry of space-time. Can two concepts, seemingly as unrelated as a subatomic particle and a cosmic tunnel, possibly be two sides of the same coin? Imagine a universe where the ethereal links of quantum entanglement are not just abstract connections, but physical bridges through space-time, shortcuts through the cosmos. It is a concept that has sent ripples through the physics community, a bold conjecture known as ER equals EPR. ER, standing for Einstein-Rosen bridge, also known as a wormhole, and EPR, referring to the Einstein-Podolsky-Rosen paradox, the very foundation of quantum entanglement. The conjecture proposes that these two seemingly distinct phenomena, wormholes and entanglement, are actually two different descriptions of the same underlying reality. Wormholes, those theoretical tunnels through space-time, have long been a staple of science fiction, offering the tantalizing possibility of interstellar travel. But in the realm of general relativity, they are more than just plot devices. They are mathematical solutions to Einstein's field equations, hypothetical shortcuts that could connect two distant points in the universe. They are, in essence, cosmic rabbit holes, offering a detour around the vast distances of space. But there's a catch. Traditional wormholes, as described by general relativity, are notoriously unstable. They require exotic matter with negative mass energy to hold them open, a substance that has never been observed and may not even exist. Without this exotic matter, the wormhole would collapse in on itself, pinching off the connection and rendering it useless for travel. So, where does entanglement come in? The ER equals EPR conjecture suggests that entanglement may provide the very fabric that holds these wormholes open, replacing the need for exotic matter. It posits that every pair of entangled particles is connected by a tiny, sub-microscopic wormhole, a bridge through space-time that allows them to instantaneously influence each other, regardless of the distance separating them. Think of it like this. Imagine two islands separated by a vast ocean. Traveling between the islands by boat would take an incredibly long time. But what if there was a tunnel connecting the two islands, a shortcut that allowed you to travel from one to the other instantaneously? This tunnel would be analogous to a wormhole, and the entanglement between the two islands would be the force that keeps the tunnel open. This conjecture has profound implications for our understanding of the universe. It suggests that space-time itself may be fundamentally quantum, that the geometry of the cosmos is intertwined with the strange and wonderful laws of quantum mechanics. It also hints at a deeper connection between quantum information theory and general relativity, two seemingly disparate branches of physics that may be converging to reveal a more complete picture of reality. Could entanglement be the very building block of space-time, the threads that weave the fabric of the cosmos together? Imagine the universe as a vast, interconnected network of entangled particles, each pair linked by a tiny wormhole, creating a web of quantum connections that spans the entire cosmos. It is a radical idea, one that challenges our most basic assumptions about the nature of reality. It also opens new avenues for exploring the mysteries of quantum gravity, the elusive theory that seeks to reconcile quantum mechanics and general relativity. Quantum gravity is considered to be one of the holy grails of modern physics. One can imagine that quantum gravity may hold the key to unlocking the secrets of the Big Bang, black holes, and the ultimate fate of the universe. But the ER equals EPR conjecture is not without its challenges. It is still a highly speculative theory, and there is no direct experimental evidence to support it. However, it has sparked a flurry of research activity, inspiring physicists to explore new theoretical frameworks and devise novel experiments to test its predictions. Could this entanglement provide a way to understand black holes and the information paradox? But the ER equals EPR conjecture is not without its challenges. It is still a highly speculative theory, and there is no direct experimental evidence to support it. However, it has sparked a flurry of research activity, inspiring physicists to explore new theoretical frameworks and devise novel experiments to test its predictions. Could this entanglement provide a way to understand black holes and the information paradox? Perhaps the key to unlocking these mysteries lies not in breaking space, but in redefining what we even mean by the word. We have thrown around the phrase breaking space quite a bit, haven't we? It's catchy, provocative, and certainly grabs the attention. But let's be clear, entanglement doesn't literally break space. No, it's not like you can use entanglement to teleport yourself to another galaxy or create a shortcut through a black hole for your morning commute. We aren't talking about physical interaction defying the speed of light. What entanglement does do is challenge our most deeply ingrained assumptions about how the universe works, specifically our classical notion of locality. Locality, at its core, is the idea that an object is only directly influenced by its immediate surroundings. The gravitational pull of the Earth keeps you grounded. The warmth of the sun comes from photons striking your skin. These are local interactions. To influence something, you need to be nearby, or at least connected by something that travels through space over time, like light, sound, or maybe a strongly worded letter. The classical world, the world governed by Newton's laws and Einstein's relativity, is fundamentally local. It's a world where cause and effect are neatly tied together by space and time. Entanglement throws a quantum wrench into this picture. It demonstrates that two particles can be intrinsically linked, their properties correlated instantaneously, no matter how far apart they are. It is like an invisible thread connecting them, bypassing the need for any physical connection or signal to travel between them. The connection is real, as we have seen, it's measurable, but it doesn't fit into our classical understanding of space and time. Think of it like this. Imagine you are watching a synchronized swimming performance on television. Two swimmers, separated by hundreds of miles, move in perfect unison, their movements mirroring each other with uncanny precision. You might assume they are communicating somehow, perhaps using hidden microphones or pre-recorded instructions. But what if there was no communication at all? What if their movements were predetermined, choreographed in advance, their actions perfectly correlated from the start? This is analogous to entanglement. The entangled particles aren't sending signals to each other. They are simply revealing their pre-existing correlations. Their fates are intertwined from the moment they are created, their properties linked in a way that transcends space and time. So, what does it mean to say that entanglement redefines what separation and distance mean at the quantum level? It means that at the quantum level, the concept of separation is not as straightforward as we might think. Two entangled particles may be separated by vast distances in space, but they are still connected by a quantum link that is independent of that distance. Their connection is not mediated by anything that travels through space. It is intrinsic to their quantum nature. They are in a sense not truly separate at all. They are part of a single unified quantum system. This is a radical departure from our classical worldview, where objects are considered to be separate and independent entities. Entanglement forces us to rethink what we mean by distance. In the classical world, distance is a measure of physical separation, a barrier that limits the speed at which information and influence can travel. But in the quantum world, distance is less of a barrier and more of a label. Two entangled particles may be separated by vast distances, but they are still connected by an instantaneous quantum link. Their connection is not diminished by distance, it is independent of it. It's almost as if space itself is a kind of illusion, a construct that emerges from a deeper, more fundamental reality. Entanglement suggests that at the quantum level, the universe is not a collection of isolated objects scattered across an empty void, but a vast, interconnected web of quantum relationships. It is a universe where everything is linked to everything else, where the boundaries between here and there, between then and now, begin to blur. This quantum interconnectedness has fascinated artists, musicians, and writers for years. The universe is not simply the sum of its parts, but a holistic, interconnected whole. While we haven't quite broken space in the science fiction sense, entanglement has broken our classical notions of space, forcing us to confront the strange and wonderful nature of the quantum world. This raises so many questions. So many. Does reality truly exist without measurement? Is the universe predetermined? It may not be possible to ever know. But one question leads to another, the same way one thing is entangled with another. But we haven't quite broken space in the science fiction sense. Entanglement has broken our classical notions of space, forcing us to confront the strange and wonderful nature of the quantum world. This quantum interconnectedness has fascinated artists, musicians, and writers for years. But what does it all mean? Is there a deeper current flowing beneath the surface of quantum mechanics? Quantum entanglement doesn't just rewrite the physics textbooks, it throws open the doors to some of the most profound philosophical questions humanity has ever grappled with. Forget about the nuts and bolts of experimental setups for a moment and consider this is our very understanding of existence about to undergo a quantum leap. What does non-locality truly imply about reality? Does it mean that the universe is fundamentally interconnected, a vast cosmic web where everything is linked to everything else? Are we all just nodes in some giant quantum network, our fates intertwined in ways we can barely begin to comprehend? Think about causality, the bedrock principle that every effect has a cause, a chain of events stretching back to the beginning of time. Entanglement seems to suggest that effects can occur instantaneously, without any apparent cause, challenging our linear view of time and consequence. It's as if the universe is playing a cosmic game of chess, where pieces on opposite sides of the board can suddenly influence each other, defying the rules of classical strategy. And what about the relationship between observer and observed, that age-old question that has plagued philosophers for centuries? Does our act of observing a quantum system somehow alter its reality? Does the universe only become definite when we look at it, or does it exist independently of our perception? Imagine a tree falling in a forest and no one is around to hear it. Does it make a sound? That's an old philosophical chestnut, but entanglement adds a quantum twist. It's not just about whether the sound exists. It's about whether the tree itself exists in a definite state before someone observes it. Is it a tree, a shrub, or a collection of quantum probabilities until we shine a light on it? Does an object possess definite properties before measurement, or is reality created in the act of observation? This is perhaps the most unsettling question of all. Does the universe exist in a state of potential until we come along to collapse the wave function and force it to choose a reality? Some physicists argue that the universe is like a giant choose-your-own-adventure novel, with each quantum measurement acting as a branching point, creating new and alternate realities. Others believe that there is an objective reality out there independent of our observations, a reality that quantum mechanics is simply failing to fully capture. The great physicist John Archibald Wheeler proposed the concept of a participatory universe, suggesting that observers are necessary to bring the universe into being. In his words, we are participators in bringing into being not only the near and here, but the far away and long ago. It's a concept that sounds more like something out of a science fiction novel than a physics textbook, but it highlights the profound implications of entanglement. Picture this. You have a sealed box. Inside, a cat is either alive or dead. According to classical physics, the cat has a definite state even if we can't see it. But quantum mechanics suggests that until we open the box, the cat exists in a superposition, both alive and dead simultaneously. It's not until we open the box and observe the cat that the superposition collapses and the cat chooses a state. This thought experiment, which is often known as Schrödinger's cat, named after Erwin Schrödinger, who proposed it to show how absurd he felt the quantum world was, if projected into the classical world, is a microcosm of the observer problem. Does the act of observation create reality, or does it simply reveal it? Is the universe a giant illusion, or a fundamentally objective entity? These are not easy questions to answer, and they may not even be answerable with the tools of science alone. They delve into the realm of metaphysics, the branch of philosophy that explores the fundamental nature of existence. The implications of entanglement extend far beyond the laboratory it touches on the very essence of what it means to be human, to perceive, to exist. What other mind-bending concepts are out there? But what are the consequences of accepting such a participatory role in shaping reality? What happens to our understanding of entanglement if we embrace the idea that every measurement creates a new universe? Buckle up, because we're about to dive into the deep end of quantum philosophy, a place where the boundaries between physics and metaphysics become delightfully blurred. Imagine a world where every choice you make, every decision you take, doesn't just alter your life, but spawns an entirely new branch of reality. Sounds like the plot of a mind-bending science fiction film, right? Well, some physicists believe this is precisely what's happening at the quantum level, all the time, in what's known as the many worlds interpretation, or MWI. This interpretation offers a radical alternative to the Copenhagen interpretation, the dominant view that we discussed earlier. Remember the Copenhagen interpretation? It posits that measurement causes the wave function of a quantum system to collapse, forcing it to choose one state from a multitude of possibilities. It's as if the universe is a game of roulette, and measurement is the act of spinning the wheel and determining the outcome. The many worlds interpretation throws out the roulette wheel altogether. Instead of collapsing the wave function, it proposes that every measurement causes the universe to split into multiple parallel branches, each representing a different possible outcome. It is like a branching tree, with each fork representing a quantum measurement. Each path represents a different version of the universe. So, when Alice measures the spin of her entangled photon, she doesn't just force it to choose up or down, she splits the universe into two branches, one where the photon is spinning up and one where it's spinning down. In one universe, Alice sees spin up and Bob sees spin down. In the other, Alice sees spin down and Bob sees spin up. Both universes exist side by side, forever separated by the act of quantum measurement. It is a mind-boggling concept, the idea that there are countless parallel universes branching off from our own, each slightly different, each representing a different possible reality. It suggests that for every choice you make, for every decision you take, there is another version of you living out the alternate scenario in a parallel universe. Did you order coffee instead of tea this morning? In another universe, you chose tea, and your life is unfolding slightly differently as a result. The many worlds interpretation, first proposed by Hugh Everett III in 1957, isn't just a philosophical curiosity. It is a serious attempt to make sense of the strange and wonderful world of quantum mechanics. It offers a compelling explanation for entanglement, one that avoids the need for instantaneous action at a distance. The interconnectedness is because the worlds are created together and always correlated. In the many worlds. Interpretation: entangled particles aren't communicating with each other across vast distances. Instead, their correlations are a result of their shared history, their common origin in a single quantum state. They are like two branches of the same tree, forever connected at the root, even as they grow in different directions. This interpretation also does away with the concept of wave function collapse. Every quantum possibility plays out, but in different worlds. It's a maximalist view of the universe, where nothing is ever truly lost or destroyed, and where every possibility is realized somewhere. It's a universe where the road not taken is just another path in the cosmic forest. Think of the implications. Does every quantum measurement create new universes? If that is true, we are talking about an unimaginable proliferation of worlds, a cosmic explosion of branching realities occurring every moment of every day. It sounds like the ultimate in parallel universes, and while MWI elegantly deals with correlations, it raises so many more questions. From a single genesis, did it all spring, or does it come from someplace else? It may never be fully understood, but the journey into the quantum world will continue forever. So, with the universe potentially mirroring our own choices in countless alternate realities, where does that leave us here now? Are we destined to simply ponder the philosophical implications of entanglement, or can we harness this quantum weirdness to shape our future? The answer, it turns out, is a resounding yes. Forget the theoretical musings for a moment. Let's step inside the laboratories, the clean rooms, the high-tech workshops where scientists are actively pushing the boundaries of entanglement, transforming it from a mind-bending concept into a tangible technology. What are the questions that consume these researchers? What are the challenges they face as they stand at the cutting edge of quantum science? Consider this. If entanglement is so delicate, so easily disrupted by the outside world, how do we scale it up? How do we create entangled systems with hundreds or even thousands of qubits, the building blocks of quantum computers? It is a monumental task, like trying to build a skyscraper out of soap bubbles. Each qubit is incredibly fragile, susceptible to noise and interference that can destroy its quantum state. One of the biggest challenges is maintaining coherence, the ability of qubits to maintain their superposition and entanglement over time. Imagine trying to balance a spinning top. The longer you can keep it spinning, the more useful it is. Similarly, the longer qubits can maintain their coherence, the more complex calculations a quantum computer can perform. Scientists are exploring various approaches to improve coherence times, from using exotic materials to isolating qubits in ultra-cold environments. What if a quantum computer can complete calculations, but the answer is wrong because of the inherent noisiness? That is where error correction comes in. Even the best qubits are prone to errors. But by entangling multiple physical qubits to represent a single logical qubit, errors can be detected and corrected without disturbing the computation. However, building such error-correcting systems requires many more physical qubits than logical qubits, hence the race to increase the numbers of entangled qubits. Think of it like having a team of proofreaders working on a document. Each proofreader reads the document independently, and if they find an error, they correct it. By having multiple proofreaders, you can be more confident that the final document is error-free. Building practical quantum networks is another major area of research. Imagine a future where quantum computers, quantum sensors, and quantum communication devices are all connected by a quantum internet, sharing information securely and instantaneously. Such a network would require the ability to distribute entanglement over long distances. Imagine the internet, but instead of just transferring information, it is also transferring the quantum entanglement between particles. Instead of having to load a web page, it is as if you and your computer are entangled with the page and you can interact with it without having to move a muscle. This is a major technical hurdle, as entanglement is easily disrupted by the environment. Scientists are exploring various approaches to overcome this challenge, including using repeaters to amplify quantum signals and developing new types of quantum communication protocols. How far can quantum entanglement reach? Right now, scientists are experimenting with entanglement and teleportation across smaller and smaller chips, but they are working on sending it up into space to be reflected back down to Earth. Think of a ball bouncing back and forth. Entanglement can also work the same way, traveling back and forth as it becomes more advanced. Witness the dynamic progress. It's a race against time, a battle against the fundamental laws of physics, but the rewards are enormous. Scientists are not just building better computers and sensors, they are building a new future, a future where the seemingly impossible becomes reality. The lab coats are on, the lasers are humming, the qubits are dancing. But where is all of this leading us? What does the future look like when we've truly mastered this spooky connection, this entanglement that Einstein found so unnerving? Forget about incremental improvements. We're talking about a potential quantum leap in technology, a transformation so profound it could reshape society itself. What if the Internet, as we know it, the one that connects billions of devices and people, was fundamentally insecure? What if every email, every financial transaction, every top-secret government communication was vulnerable to interception and decryption? It is not a hypothetical threat. It's a very real possibility in a world increasingly dominated by cyber warfare. But imagine a new kind of internet, one built on the principles of quantum mechanics, where security is not an afterthought but a fundamental law of nature. Envision a global quantum internet providing ultimate security, impossible to crack because any attempt to eavesdrop would inevitably disturb the very fabric of the quantum connection. Information would be shielded at a level deeper than mathematics, coded within the very atoms themselves. This isn't just about protecting secrets. It's about safeguarding democracy, preventing espionage, and ensuring the integrity of our digital world. But the quantum revolution goes far beyond communication. What if we could design new materials and medicines at the atomic level, simulating their behavior with unprecedented accuracy? predicting their properties before they even exist in the real world. Quantum simulators, powered by entangled qubits, promise to unlock the secrets of chemistry, materials science, and drug discovery, accelerating innovation at an unprecedented pace. What if we could design new superconductors that operate at room temperature, revolutionizing energy transmission and storage? What if we could create new catalysts that can break down pollutants and clean up our environment? What if we could develop new drugs that target diseases with pinpoint precision, minimizing side effects and maximizing efficacy? Quantum simulation could be the key, allowing us to explore the vast landscape of chemical possibilities and unlock the next generation of transformative technologies. Then consider this. The world around us is full of signals we can't detect, phenomena that remain hidden from our classical senses. But what if we could build sensors so sensitive, so precise, that they could reveal the faintest whispers of the universe? Ultra-sensitive sensor networks, leveraging the power of entanglement, could revolutionize fields like medical imaging, environmental monitoring, and fundamental science. Imagine medical scanners that can detect diseases years before symptoms appear, or environmental sensors that can detect trace amounts of pollutants in our air and water. Imagine scientific instruments that can probe the deepest mysteries of the cosmos, detecting gravitational waves from the earliest moments of the universe or searching for dark matter, that elusive substance that makes up the majority of the universe's mass. Harnessing spooky action, this entanglement that bridges space itself, how might it truly transform communication, computation, and scientific discovery? Think of a world where instantaneous communication is more than just a dream, where quantum computers solve the world's most complex problems, and where quantum sensors reveal the universe's deepest secrets. It's a plausible technological horizon shaped by quantum links, a future where the boundaries between science fiction and reality continue to blur. But it's not all sunshine and roses, is it? What if these incredibly powerful technologies fell into the wrong hands? What if quantum computers were used to break encryption codes, undermining our cybersecurity infrastructure? What if quantum sensors were used to spy on individuals or develop new and more dangerous weapons? These are the ethical dilemmas that we must confront as we move closer to this entangled future. The development of quantum technology, a path laden with tantalizing opportunities and potential pitfalls, a path leading toward destinations as yet unknown. What undiscovered secrets still lie hidden within the quantum realm, waiting to be revealed? But it is not all sunshine and roses, is it? What if these incredibly powerful technologies fell into the wrong hands? What if quantum computers were used to break encryption codes, undermining our cybersecurity infrastructure? What if quantum sensors were used to spy on individuals or develop new and more dangerous weapons? These are the ethical dilemmas that we must confront as we move closer to this entangled future. The development of quantum technology, a path laden with tantalizing opportunities and potential pitfalls, a path leading toward destinations as yet unknown. What undiscovered secrets still lie hidden within the quantum realm waiting to be revealed? Even after decades of intense research and groundbreaking experiments, some fundamental questions about quantum entanglement remain stubbornly unanswered. We have confirmed its existence, harnessed its power, and begun to glimpse its potential to revolutionize technology. But what is it really? What's the underlying mechanism that allows two particles to be so intimately connected, regardless of the distance separating them? Is it a wormhole? Is it a shared wave function? Or is it something else entirely, something we haven't even conceived of yet? Perhaps the biggest mystery of all is how entanglement interacts with gravity and the very fabric of space-time. Quantum mechanics and general relativity, the two pillars of modern physics, describe the universe at vastly different scales. Quantum mechanics governs the behavior of atoms and subatomic particles, while general relativity describes the force of gravity and the structure of space-time. Both theories have been tested and confirmed to an extraordinary degree of precision. yet they remain fundamentally incompatible. Think of it like trying to fit two puzzle pieces together, pieces that clearly belong to the same puzzle, but are shaped in such a way that they simply refuse to connect. For decades, physicists have been searching for a theory of quantum gravity, a single framework that can reconcile these two seemingly contradictory descriptions of the universe. String theory, loop quantum gravity, and other approaches offer promising leads, but a complete and consistent theory remains elusive. Can entanglement provide a key to unlocking this mystery? Some physicists believe that it can. They argue that entanglement may be a fundamental property of space-time itself, a kind of quantum glue that holds the universe together. Perhaps the universe is not a smooth, continuous fabric as described by general relativity, but a discrete, granular structure made up of interconnected quantum units. Could entanglement be the thread that weaves quantum mechanics and general relativity together? It is an exciting possibility, but it also raises a number of challenging questions. How does entanglement affect the curvature of space-time? Can it be used to create wormholes or other exotic structures? And can it help us understand the nature of black holes, those enigmatic objects where gravity reigns supreme and the laws of physics as we know them break down? What about the nature of time itself? Entanglement seems to defy our conventional understanding of cause and effect, suggesting that events can be instantaneously correlated across vast distances. Does this mean that time is not as fundamental as we thought? Does it mean that the past, present, and future are somehow intertwined in a way that we do not yet understand? These questions are not just academic exercises. They touch on the very essence of what it means to be human, to perceive, to exist within this vast and mysterious universe. As we continue to probe the depths of quantum entanglement, we are not just unraveling the secrets of the atom, we are unraveling the secrets of reality itself. Perhaps, somewhere within the strangeness of entanglement, lies the answer to some of the universe's most enduring puzzles. Perhaps the answers are closer than we think, hidden within the equations, the experiments, and the ongoing quest to understand the quantum realm. The journey continues, fueled by curiosity and driven by the unwavering pursuit of knowledge. As our journey into the quantum realm draws to a close, we find ourselves standing at the edge of a new frontier, a place where the known laws of physics seem to bend and twist, where the very nature of reality is called into question. It's been a long and winding road from the initial bewilderment of superposition and wave-particle duality to the mind-bending implications of non-locality and the potential for quantum technologies that could reshape our world. We've explored how Einstein, Podolsky, and Rosen challenged the completeness of quantum mechanics, how Niels Bohr defended its bizarre implications, and how John Bell devised a theorem that allowed us to test the reality of spooky action at a distance. We have witnessed Alain Aspect's groundbreaking experiments that confirmed entanglement, shattering our classical intuitions about cause and effect. We've marveled at the possibility of quantum teleportation, imagined the power of quantum computers, and glimpsed the potential of quantum sensors to detect the faintest whispers of the universe. But as we reflect on this journey, it becomes clear that entanglement is more than just a scientific curiosity. It's a philosophical enigma, a cosmic riddle that challenges our most fundamental assumptions about the nature of reality, space, and information. It forces us to grapple with questions that have plagued humanity for centuries. What does it mean for two particles to be linked across vast distances? Does the act of observation create reality? And what is the ultimate fate of the universe? It is like standing at the edge of a vast ocean, gazing out at the horizon, wondering what lies beyond. We have mapped the coastline, charted the currents, and explored the depths, but the ocean itself remains a mystery, full of hidden wonders and uncharted territories. Perhaps the greatest lesson of entanglement is that the universe is far stranger, more interconnected, and more wonderful than we could have ever imagined. It challenges us to abandon our preconceived notions, to embrace the weirdness, and to be open to the possibility that reality may be far more complex and nuanced than our classical intuitions allow. Entanglement is a reminder that the universe is not a clockwork mechanism ticking away according to predetermined laws, but a dynamic, ever-evolving system where anything is possible. The implications of this quantum interconnectedness extend far beyond the confines of the laboratory. It touches upon our understanding of consciousness, our relationship to the cosmos, and the very nature of existence. It suggests that the universe may be a vast, interconnected web, where every particle, every atom, every galaxy is linked to every other, a symphony of quantum relationships playing out across the vast expanse of space and time. The journey to fully understand entanglement is far from over. New experiments are being conducted, new theories are being proposed, and new discoveries are being made all the time. But even as we push the boundaries of our knowledge, we must never lose sight of the profound philosophical implications of this bizarre phenomenon. Entanglement is not just a scientific puzzle to be solved, it's a cosmic mystery to be contemplated, a source of wonder and inspiration that can transform our understanding of ourselves and the universe we inhabit. The spooky link continues to beckon us towards a deeper understanding of the universe, a deeper understanding that may ultimately challenge the very fabric of what we consider real. And so the adventure continues, promising to be even stranger and more mind-bending than what we have witnessed thus far.